So first of all, thank you, Paul, for the invitation to give this seminar. So the title is Relativistic Four-Fermi Theories, and as usual, this is a collaboration with, in this case, mostly young people from Jena and Frankfurt, with the exception of Mark Wagner, which of course is senior in Frankfurt. I will a little bit give an introduction why and where we study relativistic Four-Fermi theories. Next topic will be inhomogeneous phases in this type of models. Then I will be more specific and consider one model. At the end, I will tell you how it generalizes to other Four-Fermi theories. And I end, of course, with some conclusions and some remarks on what may happen if you switch on a magnetic field. Now, if you study scattering of, let's say, electrons or quarks, of course, this is described by gauge theories nowadays, and the exchange is by a gauge boson. For example, in QED, you can then, so let's look at this diagram here. In QED, you can integrate out all the virtual photons. It has been done one of the last papers by Richard Feynman. And what you end up is a sort of an effective interaction between the fermions. And in QED, again, you can work it out exactly because it's a Gaussian integral. And what you get is a non-local current-current interaction. So J mu is the electromagnetic current density. So you get, in this case, a non-local Four-Fermi theory. Now imagine that this is not necessarily a photon, but a heavy gauge boson, like in the electroweak interaction. And assume that the typical momentum are much less than the mass of the exchange particle, then you can approximate this diagram by a point interaction. And so, in other words, this kernel here becomes local, becomes a contact interaction. And then you end up with what nowadays we call a Four-Fermi theory. You may change, so to say, the point of view and say, well, let's describe weak interaction. Later on, I will talk about the strong interaction by an effective low energy theory. Then you just write down all operators which are compatible with your symmetries. And of course, counting the dimensions. And so you write down all tensors which you have, which are quadratic in the fermions, for example, a scalar-scalar interaction, this S, or scalars or pseudoscalars, and so on. And then you just write down all possible Lorentz invariant Four-Fermi interactions. These are these L interaction terms here. Of course, in some cases, you would like to have also parity, which further reduces the number of terms you can write down. For example, the old Fermi theory, the effective description of the Weinberg-Saller model, you have this particular current entering your theory, which couples the electrons to the neutrino field. This is famous V minus A coupling. Now, these theories, these Four-Fermi theories, are not renormalizable in the usual perturbation theory above 2 space-time dimensions. But never mind, we only use them as effective theory, which should describe the underlying gauge theory up to a certain cutoff. Okay, so there's always a unitarity limit up to which you can trust, or almost up to which you can trust your approximation. A similar story in QCD. Let me not talk about confinement here, but more concentrate on the chiral symmetry or the chiral symmetry breaking. So if you take QCD in the chiral limit of light up and down quarks, then you have an SU2 chiral symmetry, which is spontaneously broken by the chiral condensate. And again, you can write down a Four-Fermi theory, which catches part of the dynamics that come back to that of QCD. Now, this diagram or variant of it you have seen many, many times. This proposed phase diagram of QCD, temperature versus chemical potential for the baryons. And most of it you know very well, but let me now a little bit concentrate on this low temperature intermediate values of the chemical potential, where there are conjectures that there could be a crystalline phase, an inhomogeneous phase, where the baryon density forms a crystal. And now this conjecture is partly based on model calculations, and part of this talk will be about the status of these calculations. It has changed actually what we believe happens here in the last years. Okay, so this is this crystalline structure. Let me not spend too much time on it. Now, the problem, of course, is if you want to do, you understand this part of the phase diagrams, there are some problems. For example, in the lattice approach, there's this infamous sign problem that we cannot do really simulations for chemical potential, which are not very small, because the determinant is complex and the reweighting fails in this domain. Well, maybe then you can use functional methods, which has been done, especially the last years. I will try to go to larger chemical potential. But I'm not sure how reliable these results are, because there are some complications involved. There's a cutoff dependence and so on. There may be another approach again in the sense of effective models. You write down low energy effective models compatible with the symmetries and study these models. And some of these models, in particular with insight to the chiral properties, are the Four-Fermi models. I mean, they lack confinement because you have left too much of the gluonic part away, so to say. But they should describe the chiral properties of strong interaction. So let me just show you two of these sort of models which are on the market. One is a Lambo-Jean-Larsigny model. It's actually the oldest Four-Fermi theory. And it contains a field with two flavors. You see light up and down quarks, and then you have the usual kinetic term and a Four-Fermi interaction, and you write down a Four-Fermi interaction which carries this SU2 cross SU2 symmetry of QCD in the chiral limit. As I said, this theory is non-renormalizable, and what is then later on is important. You can write down a completely equivalent formulation with terms of auxiliary fields. In this case, it's the sigma fields and the pions. And the price you pay is that the Dirac operator is not a free anymore, but the Dirac operator contains these auxiliary fields, and then additional square of this auxiliary field. Also, not only classical, I mean, you can show the equivalence by just solving the equation of motion for sigma and pi and putting it back into the Lagrangian. But this is also true quantum mechanically, because these integrals of the auxiliary fields are Gaussian and can be done. And if you do that with the red Lagrangian, you end up with the blue Lagrangian in the first line. This model is not, as I mentioned, is not renormalizable. But again, it should be an effective theory, so it should be okay. Now, another model which has been studied a lot is a quark method model. Is a sort of a generalization of this Jean-Larsigny model in this auxiliary field representation. Namely, you add a kinetic term for these auxiliary fields, and the Dirac operator is still the same, and you in addition add a 5-to-4 interaction. It's safe interaction for the scalar field. So this quark method model is now renormalizable, but suffers from Landau poles. So these are the models we typically use if you make prediction about the phase diagram based on effective theories. Now let me skip this one. We here in my group in Jena, we were very much motivated in studies these Four-Fermi theories in lower dimensions. The motivation came from solid state physics, in particular from what we call Dirac material. Which have relativistic dispersion relations near the zero of the dispersion relation. Okay, let me skip this one. Okay, so let me be a bit more specific now. So we think we have some sort of Four-Fermi theory. So again, it's sort of a free part, the free theory, which includes the chemical potential. And of course, you know, if I do thermodynamics or quantum statistics, I automatically have to work with the Euclidean version of the theory. So you always work with Euclidean version of the theory because you want to discuss quantum statistics of the model, discussing phase diagrams and so on. And this is like the interaction term, which contains some Four-Fermi interaction, which I don't specify at the moment. So let me go not only work with two flavors, not only with up and down quark, with NF flavors. This allows us to study certain limits. In particular, we will study the limit NF going to infinity, where the models are, well, more tractable, let's put it this way. Okay, then when I write down a bilinear, it's always understood that we sum over all the flavors. For example, here in the free part, in the non-interacting part. Now we do thermodynamics. So we study the canonical partition function containing the inverse temperature beta and the chemical potential. And it's a path integral. It just means that the mu enters the Lagrange, that like in the first line, the mu couples to the baryon number density, and the final temperature is implemented by imposing antiperiodic boundary conditions for the fermions with period beta again the inverse temperature. And whenever we have a bosonic fields, for example, these auxiliary fields, then they should be periodic. Then we want to calculate expectation values, and in this path integral formulation, it's one of these partition functions, and again, a path integral, but now with this inversion of the operator. Some general remarks about this class of Four-Fermi theories of these interactive fermions. After John de Lassinia wrote their seminal paper, there was another famous paper by Gross-Neveu in which they started a particular Four-Fermi theories, but now in 1+1 dimension, again to learn more about strong interacting field theories. This is an asymptotically free theory. It's renormalizable. And generally, Four-Fermi theories in 1+1 dimensions are typically integrable. Sometimes they're even solvable. For example, the massless Thirring model can be explicitly solved. You can write down the Green's function. It's a prototype of a conformal field theory. In three space-time dimensions, this theory are not renormalizable in usual perturbation theory, but they are renormalizable in the large NF expansions. These are predictive theories. And actually, they are maybe even the most simple realization of the so-called asymptotic safety scenario. So many people, including myself, believe that gravity is asymptotically safe. So it's not renormalizable in perturbation theory, but it may be renormalizable in a different sense, that there is a certain fixed point with certain properties. There's a fixed point with certain properties. Now, in 4 dimensions, most of this theory are not renormalizable and used as effective theories. Later on, we will study such models in the lattice approach, and there have been earlier papers where people studied the masses of the light particles, phase diagrams, studied the sign problem, and so on. What may be interesting in hindsight of strong interaction theories, for example, gauge theories in the conformal window, is that it's very important which type of fermions you use, also for these Four-Fermi theories that we have learned. I mean, for example, staggered fermion may be very problematic, that we have learned from studying the Thirring model in 3 dimensions. But that's another story. Now, let me take as the simplest of probably the simplest of all Four-Fermi theory, or the second, maybe the Thirring model is simpler. The Gross-Neveu model, to be specific, but again, many results hold for more general Four-Fermi theories. So this is again the usual clinical term here, the chemical potential, and the Four-Fermi interaction is a scalar interaction in this case. So it's just psi bar psi, which again includes the sum over the flavors squared. And again, you introduce auxiliary field, and you get end up with this equivalent Lagrange. And again, here's the canonical ensemble, expectation values, and now we introduce the coupling in this way that so the tooth coupling in such a way that when you integrate over the fermions, and since you have NF species, NF flavors of fermions, you get the determinant to the power NF, which means in the exponent you get a factor NF times log determinant, and you get another factor NF from these parts, integral over sigma squared. So altogether you have to integrate after getting rid of the fermions, right? You get an effective action containing log determinant of the fermions. You get a factor NF in front of the effective action. Okay. The next thing we will need is that there's an exact Schwinger-Dyson equation relating the chiral condensate to the condensate of the sigma field of this auxiliary field. So instead of calculating this psi by psi condensate, you can equally well calculate the expectation value of this auxiliary field. They are essentially the same. But now look at this. Yeah, sure.
So from the notation, it's not clear to me whether, so you have the expectation value of psi bar of x and psi of x. So usually I would interpret this as being a correlator that has no x dependence because, well, they are evaluated at the same point x, but you have an x on the right-hand side. Is that intentional?
You mean on the last line or no?
Yes.
Yeah, I mean, well, first of all, the sigma a priori could depend on x, right?
If you have the psi's evaluated at the same point?
Yeah, psi bar x, psi x, a condensate at a given point x.
Okay, so usually when you have a quadratic action, that means that only the difference between the arguments appears on the right-hand side, right?
Yeah, but again, on the left-hand side, it's really the same point x and x, and this is just an identity. If it would be x and y on the left-hand side, then it would depend on the difference, I guess. Yes, you're right. But I want to have to calculate the condensate at the moment. Look at the condensate,
okay.
Right? Yeah.
Okay.
Okay, but this x dependence actually is an issue now. Very good. Okay, but now let's look at this form for the partition function, or you get a similar formula for the expectation value. It's the number of flavor times this effective action depending on this auxiliary field sigma. Now let's assume that NF is very big, and then you see, of course, at least if the effective action is bounded below, that this integral localizes, right? If NF goes to infinity. So you just have to look for the minimum of the effective action, and this then solves the path integral in this limit. That's a large NF limit. So in the large NF limit, the partition function and also the expectation values are just given by a minimizing principle. You just take the effective action, which it's written here again, is the sigma squared, which you had before. And now integrating on the fermion produces log determinant of the one flavor system, because the NF flavor, the number of flavors is in front of the minimum here. Okay, so we have to, just to minimize, well, just this is, you have to minimize this effective action. And if you have done that, actually that's it, right? Then you know what is a partition function, you can easily calculate expectation values and so on. Now we have learned almost in school, but during our studies, that the equilibrium states should be translation invariant in space. Okay, it's homogeneous. Now, if this is the case, if this state sigma bar here is the sigma hat is homogeneous, then this minimum must be homogeneous as well, must be constant. Okay, so under the assumption that the system is homogeneous, you may assume from the very beginning by the minimizing principle that the sigma is homogeneous. But then, of course, log determinant, the Dirac operator contains the sigma field. If the sigma field is constant, you can calculate this effective action. It's proportional to the volume of space-time times the effective potential. I rather should say it's more the free energy or yeah. Okay, so for homogeneous sigma, for constant sigma, we know in the large NF limit how the system behaves. We can solve it. We can calculate the phase diagram at least as long as we assume homogeneous phases. Now, I don't say that calculate this determinant is completely trivial, but anyway, it can be done by various means, at finite temperature, finite density, and so on, and has been done a long time ago. So let me a little bit summarize what we find. Okay, so again, if you only have homogeneous phases, everything is essentially known. So the question is it really true that in equilibrium, the condensate is constant? No? Is it really true that this sigma, this expectation of sigma, does not depend on X, this condensate? And well, 15 years ago, or 10 years ago, if you would have asked me, I would say, of course, it's constant. But the story is actually quite interesting, what happened then. It has been realized that the Gross-Neveu model in 2 dimensions, in this limit where one really could analytically tackle the problem, people could show that there is an inhomogeneous phase. So mathematically, what it means, if you minimize this effective action, the minimizing sigma is not constant, but it is space dependent. Okay. Okay. And I should also say this minimizing sigma, that's also part of the large NF. This expectation value of sigma is then equals to the minimizing sigma. This, if you minimize the effective action, this minimum is then exactly the expectation value. Now, this is a very recent result now. So we are always asking ourselves, people who are working in this field, so what happens if you increase the dimension? Are there still inhomogeneous phases? Now, recently, especially a group in Frankfurt, which we are collaborating with, could show that between 2 and up, but not including 3 dimensions, there is an inhomogeneous phase, okay, which exactly in 3 dimensions goes away and is absent up to 4 dimensions. So this T is now a space-time dimension here. So the last one is not really proven, but the answer is it's probably no. So it's easier to show the existence of the inhomogeneous phase than the absence. So this was one line of reasoning, but all these results were only obtained in the limit NF going to infinity. You don't have to solve the full functional integral, but you could sort of minimize this effective action. So it's really a question treating this log determinant in a proper way for inhomogeneous backgrounds. The other type of question was, what happens if you go away from the NF going to infinity limit? Is all these inhomogeneous phases are these artifacts of the NF going to infinity limit? Now, for example, if you take not the Gross-Neveu model, but a related model which has a U1 symmetry, the current Gross-Neveu model, in the large NF, you also get inhomogeneous phase, but we know it cannot be because of Mermin-Wagner, right? In this case, we break translation invariance, which is a continuous symmetry. And Mermin-Wagner tells us this should not be possible. And the way out was always, well, Mermin-Wagner doesn't apply if NF goes to infinity. That was the explanation why one sees this inhomogeneous condensate which breaks translation invariance. Just a word of warning, Mermin-Wagner, or if you want the Coleman theory, does not always apply the way we have learned it. It depends on the dispersion relation for the particles. So if you have a chemical potential or dispersion relation, it becomes non-relativistic and the theorem changes. It's just a word of warning. But still, I mean, there was always this discussion, is this really an artifact of NF going to infinity, these inhomogeneous phases? Now, we have looked at that and studied now with Monte Carlo simulation these theories at NF less than infinity. And in D equals 2, we still found inhomogeneous phases. I will come to that. And so this is this yes in quotation mark. And we have some results in D equals 3 dimensions as well. Okay, so this is again yeah.
May I ask a question?
Sure.
Is there a way to calculate the condensate in the inhomogeneous phase? Or how do they show the existence of inhomogeneous phase?
I come to that. Let's just wait.
Okay.
Yeah. So let me.
How do you? Okay.
Yeah. That's of course that's interesting. Yeah. But let me. I come to that.
Okay.
Okay. So let me tell you a bit more about the story. First, in this one-dimensional, actually beautiful result, where people could prove that there's an inhomogeneous phase in the larger NF unit. So the other results were for homogeneous background, homogeneous fields, and then what you find is a second-order phase transition from a homogeneously broken phase to a symmetric phase. And then there was a point, an end point, where these second-order transitions end, and it continued with first-order transition. This is this broken red line. Okay, so that was the situation up, I forgot, 1998 or so. And then people realized there is this inhomogeneous phase in 1+1 dimensions. So this first-order line is replaced by two second-order lines, this orange one, and the orange one goes from the homogeneously broken phase to an inhomogeneous phase, where the condensate, so to say, is periodic. It forms a sort of a lattice. Again, I come back to that. And there's a green transition from the inhomogeneous phase to the symmetric phase. So the first order line is replaced by two second order lines, and it opens up, so to say, it forms an inhomogeneous phase, which goes to mu going to infinity, but of course to lower and lower temperatures. Now here, finding the minimum means solving the gap equation. That comes now to answer your question in 1+1 dimensions. So people could solve the gap equation exactly, and the solution of the gap equation was given by elliptic functions. They use some sort of supersymmetric structure of this gap equation, and I think it's a beautiful piece of mathematical physics that was done by Thies and collaborators in Erlangen, actually 20 years ago. This doesn't work in higher dimensions, and again, I come to that. Okay, now what is the situation in three space dimension? That's the second diagram. So if you just have homogeneous fields, then what you find is a second order line which go all the way down to temperature equals 0. Everything is second order. And only at t equals 0, we have it's actually funny, the effective potential is really absolutely flat. So, so that you can say this is sort of a first order transition, but it's the very end of this line of this, okay. So, and up to now in 3 dimensions, nobody has seen an inhomogeneous phase, and we are sort of convinced there is none. Again, and I told you there are inhomogeneous phases below 3 dimensions, and I will mention how it has been found in a moment again. Okay. I should mention that if you keep your cutoff in your theory, or if you work on a lattice, then you may have an inhomogeneous phase. Then we have seen that actually. There are inhomogeneous phases if you don't remove the UV cutoff. And that's, of course, essential for solid-state physics, where you don't remove the cutoff. I mean, the lattice, so to say. You have a finite lattice constant, and then it has been observed in the lab, there are inhomogeneous phases. Okay. Now, you could do the following in the phase diagram. You would you look for you minimize this effective action. Now this is done here numerically, still in 1+1 dimensions, and you just look whether the energy of this configuration, so that these all are where the algorithm stops. These are metastable states, and some of them are stable, and these configurations are stable. Is the effective potential multiplied by 4 pi is less than -1, because -1 is the minimum on the homogeneous configuration in this normalization. So you see the top left, mu is equals 0. We have a configuration, a kink double, kink anti-kink, but the energy is higher than the homogeneous, the minimum, homogeneous minimum. So this is a metastable state. It's a baryon-antibaryon, right? It's interpreted as a baryon. And you can calculate the difference of energy between this configuration and the homogeneous. And from that, you can calculate just the mass of the kink anti-kink, which is exactly what we know is from the analytic solution. It's this second to last line. Then you go further down. The effective potential is still a bit higher than the homogeneous. So the left bottom is still a baryon-antibaryon, a kink-anti-kink. But then on the top right, or on the right-hand side, these combinations are stable. They have lower energy than the homogeneous ones. And they would then form a crystal. Right? This is then really the thermodynamic equilibrium state, has low energy than any homogeneous configuration. And this is the stable equilibrium state. And again, depending on the chemical potential, if the chemical potential increases, the wavelengths get shorter and shorter, the amplitude gets smaller and smaller. And finally, if you increase the temperature, the amplitude goes to 0, and you go to a second phase, to the symmetric phase. But that is a well-known situation in 1+1 dimensions. That people study now the system in dimension between 2 and 3. And I show you 2 points again. You confer everything to momentum space, and then you have drawn integrals in which you can make a continuation in the dimensions. So that's how you go to broken dimensions, so fractional dimensions. So in 1+8, I should say space dimension of the space-time is 2.8. Again, we see this yellow second-order phase transition. We see this Lifshitz point, and the blue line again is a transition, second-order transition between inhomogeneous phase and homogeneously broken phase, and so is the green line. Okay, so then you see here there's again a inhomogeneous phase between the blue and the green line, and it's getting smaller, right? And then you increase the dimension, and if you go to 3.5 space dimension, it's gone, the inhomogeneous phase. Now that's again shown in the lower plot. You see this Lifshitz point where so to say, where the inhomogeneous phase emerges. And then if we increase the dimensions from 2 space dimensions to 3 space dimensions, then here it rapidly disappears, the Lifshitz point. So there's no inhomogeneous phase anymore. There's no mode regime anymore. And the situation looks very much like shown here on the top. So there is no inhomogeneous phase. Okay. So how has it been done? So what people do, so this was not done in Jena. This was done in Frankfurt. There were lots of discussion, but it was done by Panullo and Königstein. Königstein is in Jena, actually, Panullo in Frankfurt. So they start with the symmetric phase and perturb it by inhomogeneous configuration. So you look for the second functional derivative of the effective action, which is given by some operator. And then you essentially study the spectrum of this operator and see whether there's a negative mode, an unstable mode. That's what you do. That's not easy because it's really sort of, at the end of the day, you have to look for a log determinant and its second functional derivative and this operator. And we only look for fields which are modulated in 1 dimensions, right? To simplify the problem. And then again, you just look for the second derivative at sigma equals 0, which means the perturbation of the symmetric phase. And this can be studied numerically. So this is what you were asking for, you make a stability analysis. This doesn't work if you perturb the homogeneous condensate, because we know that this is not smoothly connected to the inhomogeneous phase. Okay, so that is the story in the large NF limit. So in this effective model. And actually, it's not only true in the Thirring model, it has also been in the Gross-Neveu model. It also has been investigated in other Four-Fermi theories. It seems to be a general feature that the inhomogeneous phases in this large NF limit go away if we approach three space-time dimensions. It's an interesting question. What is the reason for this critical dimension tree? We don't know the answer. Okay. I should mention, this I already mentioned, if you with UV cutoff, one recovers for certain models in homogeneous phases. And what is also a little bit unusual, if you go to finite volumes, you believe that finite volume increases the fluctuations, and there should no inhomogeneous phase in this case. Anyhow, but it's not true. For fermions, the system behaves a bit differently. So we have seen that in finite volumes, you may again get inhomogeneous phases. Next topic, which we have been working on, but which I'm not talking about, includes strong magnetic fields. Because if the magnetic fields are very strong, you see something sort of like a dimensional reduction by 2 dimensions. So if you study a 4-dimensional model, it behaves like a 2-dimensional model, and there may be a chance to find inhomogeneous phases. So I think this is a potentially very interesting scenario. Again, you take a realistic 4-dimensional effective theory, switch on a strong magnetic field, then it may very well be that you find inhomogeneous phases. So again, we have some results on that, but let me skip it here. Okay, now this is again shown the phase diagram in 3 dimensions. I think I have explained everything. It's just a different representation of the previous result. Okay, so this is roughly the story in the limit NF going to infinity. So what happens if you go away from NF going to infinity? So realistic number of flavors 2, let's say. Well, we started again going down to one dimensions and see what happens. Does this result of T's and collaborators still holds if the number of flavors is small, let's say 2 or 8? Because you remember the story about the Goldstone theorem, which is now valid, should be valid for 2 flavors, or finite number of flavors. Now you go to your write your code, which of course we have here for all kinds of theories, and put now taken this Gross-Neveu type model, which chemical potential not equals to 0, finite temperature, here mu is equal to 0.5, temperature 0.036, where the scale is given by the condensate at 0 temperature. And then you find such a typical configuration. That was the first thing we have seen many years ago. So you see this Euclidean time going up, and to the right it's the space direction. Okay, on the lattice. And then you see there's there are stripes in this typical configuration. So it looks like, could be something like, this one here, which you see, this crystal type structure. And this was, I think this was for 2 flavors, if I remember correctly. So we said, well, there seems to be some trace of homogeneous structures, even for a small number of flavors. But then we look more carefully into this model, and then later on in this 3-dimensional model. So, we integrate out the fermions. Then we are left with this effective action, log determinant of the Dirac operator, again this quadratic term of the auxiliary field, but now put everything on the lattice. Now, we are interested in the chiral properties of these models. We want to study chiral condensate, in particular inhomogeneous condensates. And then, of course, as some of you may know, that that's an issue, which type of fermions you use on the lattice. If you discretize the model, probably shouldn't use any fermions with break chiral symmetry drastically. So what we used is so-called slack fermions, and later on in this magnetic field we used overlap fermions. And sometimes if you just took the number of flavors, multiple of 8, then you can take even naive fermions. which have doublers, but then you just describe more flavors than you may like to describe. Okay, so all these determinants are chiral. And then you produce many ensembles on the grid, so in temperature and chemical momentum space. You make, finite size analysis, you make continuum limit, and so on. So that's all standard. Important is really that you have chiral fermions, which means that the simulations are not that cheap. That was reason we first spent some time in 1+1 dimension. Okay. Now, you can, for example, study the expectation value of the auxiliary field squared. We don't take sigma. I mean, this is very known in the lattice community because on the finite volume, the expectation value of sigma is always 0 for ergodic algorithm. You have to take the modulus of sigma or sigma squared to see spontaneous breaking. Okay. And so this is a typical phase diagram. You come up with, again, chemical potential versus temperature. And then you see this histogram where we have the red color. We have spontaneous non-trivial condensate. And the green one is almost 0. Of course, it's never 0, the sigma squared, but it's very small. So you see here what is expected, that the two homogeneous phases, the broken phase and the symmetric phase. Now, this observable is not good enough to discriminate between homogeneous condensates and inhomogeneous condensate. So instead, we looked at this correlator C, and actually this was very important for our work to come up with a correlator, a suitable correlator which can really measure the inhomogeneous structures in the theory. So we looked at the sigma field at the position X correlated with the sigma at the position 0. The second line, the second part is just for statistics. You sum over variables on which it should depend and divide by the number of terms in the sum. Okay. Now again, if I calculate the expectation value of sigma on the finite lattice, it's always 0. And so you must be careful that you don't calculate a correlation function which shows you inhomogeneous structure, but which for the same reason as sigma is 0, also vanishes. And this correlation function here is of this type. It catches inhomogeneous structures, but it's not washed out by these collective coordinates, which translates the sigma field over the lattice. Okay, now we also studied the Fourier transform of these two-point functions. So what do we expect? If you have a symmetric phase, then the typical field configuration fluctuates around 0, and this Fourier transform just has a small amplitude for any values of k. Now, if you have a homogeneous broken phase, then sigma is constant. So that means the k equals 0 is pronounced, it's enhanced, that the k equals 0 mode. So we expect in the Fourier spectrum a distinct peak at k equals 0, means a homogeneous broken phase. Now, if you have an inhomogeneous phase, so these phases are, the condensates in the analytic solution almost look like sine, cosine. They are not, but they almost look like harmonic functions. So we expect that there are peaks at momentum which are not equal to 0, right? That's some dominant wavelengths. So then you do these simulations, and here on the left you see sigma mu equals 0 baryon density, and temperature small, blue, where we expect a homogeneous broken phase. And you see that, oh, that was not good. Yeah. You see the blue, which is saddle Z1, which again we interpret as a homogeneous broken phase, and high temperature is this orange curve, which goes to 0. And you look for the Fourier transform. Indeed, the blue has a peak at 0, and the orange is essentially almost small. Okay. Then on the left bottom, we see very low temperature, but we increase the chemical potential. So we are always in the inhomogeneous phase, and you see if you increase the chemical potential, then the amplitude goes to 0, and the wavelength shortens. that's the same as in the homogeneous, in the analytic solution. And you see the Fourier transform, two peaks, and the peak is very pronounced, more pronounced at low density and gets weaker at high temperature. And finally, if the chemical potential is further increased, we go again in the symmetric phase. Well, this is more for the lattice people. We checked, of course, that we are close to the continuum limit, checked for finite size effects and so on. And so let me get the, yeah, okay. So this is a bunch of phase diagrams. To the right, you go to the continuum limit. To the bottom, you go to infinite volume. Along the diagonal, you go to the continuum limit with a constant physical size of the system. So you can see the blue domain is the inhomogeneous phase. Okay. The red again is the homogeneous, the broken phase, and the green one is the symmetric phase. So what you see is even in the continuum limit, we have a leftover of this blue inhomogeneous phase. I mean, this is just summarizing the results. Now the question was about the Mermin-Wagner theorem and long-range correlation. So we did really a simulation of extremely large lattices, up to 700 lattice points in the spatial direction. And what we wanted to see, this two-point function, whether it goes to a constant, that would mean that we are in the homogeneous broken phase, so that we have long-range order, that we have a crystal, or that it decays algebraically, which means that we have almost long-range order. This is the BKT phase, which we have sometimes in 2 dimensions. And actually, also we went to have these huge lattices. The analysis was not conclusive. We couldn't really distinguish whether it's a BKT phase or whether it's really a crystal. Now, from other calculations, analytic calculation, we know that it is a BKT phase. But if you think about applications, and Rob was very much interested in this result, Pisarski, you can make estimates with your parameter. And if the decay is extremely slow for the phenomenology, it may not really matter whether it's really a crystal or whether it's a almost crystal in the sense of decaying very, very slowly, these inhomogeneous structures. Okay, now there are other checks, barrier number, looking for crystals. Let me maybe skip that one. Yeah. Okay, then you could, of course, study more general Four-Fermi theories. The next step you could go is by including another additional term, such that the model has now a continuous axial symmetry. And in this case, the condensate would really break this symmetry. And this really should not happen in 1+1 dimensions. So again, there's a Bosonization with term of auxiliary field. In this case, you have a scalar field and a pseudoscalar field. Again, you have this word identity of the Zwinger-Dyson equation relating the condensate to the delta field, but delta is a complex field now, sigma plus IP. And the analytic result exists in 1+1 dimension in the large NF limit. So the phase diagram is sort of boring. So there's an inhomogeneous phase for low temperature of any chemical potential. And there's a symmetric phase for high temperature, but any value of the chemical potential. So this is a phase boundary. It's really a constant line with constant critical temperature. So in the analytic result, this is sort of the effective potential has a minimum at the origin in the upper part in high temperature phase. There's a minimum away from the origin in the low temperature phase, but the condensate winds, so to say. So it forms a chiral spiral. So that's how it's called. So I mean, if you go along the X direction, then this complex field really winds and it forms this sort of spiral. Okay, now we again do simulations at finite number of flavors, and this was 8 flavors, I guess. Yes, and what you see at low temperature, again, this is a histogram of the sigma field. We have this ring structure, and then you increase the temperature going to the right, and further increase the temperature. And finally, you know, the histogram shows that the fields are near the origin. So you would say here there's some sort of breaking, and on the right and down, that's a restored phase. This is just for your eyes, so to guide your eyes. This is it's just a configuration, a typical configuration. What we have shown here is these correlators here. Again, you have to think about correlators which catch the inhomogeneous structures. So these are now correlators between the sigma and the pi field. The structure is again the same, the space-time structure. And you can do the same with the sigma and sigma field. And you can convince yourself these two correlators should catch really this ring structure. So that is what is shown here. Here's the x coordinate. Here's the sigma pi correlator, the sigma sigma correlator. And what you see again is this structure, this sort of chiral spiral. And this is now even at 2 flavors. So, you know, very, very small number of flavors. Okay, and on the right, you see the 2 correlators individually. And so there seems to be, again, an inhomogeneous structure. And so then we started this Four-Fermi term, which again, by order density is given by this 2-point function of this complex auxiliary field. And there has been conjecture by Witten, calculation in a related model in some approximation, that this correlator should decay algebraically with the distance. And so we checked for this one, and we found a nice agreement. So that's again a BKT phase at any finite temperature, and at 0 temperature. It is a BKT phase at 0 temperature and very low temperature, and then it goes into a massive phase if you increase the temperature. Okay, I skipped some part, but time is anyway, it's running. So let me instead summarize, and if you have questions about higher dimensions or magnetic field, we can do that later. Okay, so anyway, what I have shown you it is the first simulation which have been done for Four-Fermi materials with chiral fermions. Okay, at finite temperature and finite chemical potential and a finite number of flavors. There have been other simulations with chiral fermions by Simon Hansen, or also in our group for the Thirring model in 3 dimensions. Yeah, we were interested in the critical properties of these models and the critical flavor number and so on. But for models with finite chemical potential, these are the first simulations with chiral fermions. So we have calculated the phase diagram of the chiral Gross-Neveu model of the Gross-Neveu model in 1+1 dimensions, and found a quasi long range order. So for any practical purposes, we found, I would say, a crystal of baryons. In the chiral Gross-Neveu model with this U1 symmetry, at least at very low temperature, we could see the chiral spiral, even for 2 flavors. For 8 flavors, even more. Okay. Now, what we have seen in the stability analysis, that the inhomogeneous phases shrink with increasing number of flavors. Oh, sorry, no, this was a lattice simulation. This is final number of flavor. So the inhomogeneous phases, the region where we have inhomogeneity, shrink with increasing number of flavors. That's expected, because if you increase the number of flavors, you have less fluctuations in the fermionic sectors, and this means that really the order, it's just wrong here. It should be the other way around. The inhomogeneous phase decreases, of course, shrinks with decreasing number of flavors, because if you decrease the number of flavors, the fluctuations increase, which destroys order. Okay. So we could calculate the baryon mass of the lattice. We have seen a quasi-baryon crystal and a chiral spiral, and observe this quasi-long-range order. Okay. Now, we have done simulation in 2+1 dimensions. We have not seen an inhomogeneous phase. That is an agreement with a large NF calculation, which I discussed. And it's expect, again, in the large NF, if you don't find inhomogeneous phase, you should not expect to see them at finite NF, because again, the fluctuation increase if you decrease the number of flavors. And well, it just destroys and not creates crystalline structures then. Okay, so no, we haven't seen any inhomogeneous phase in lattice simulation in higher dimensions. The story is different for strong magnetic fields because of the dimensional reductions. And the story, astonishingly to me, is also different in finite volumes. We have seen islands of inhomogeneous phases which then go away in the infinite volume limit. So the question to me is, what is special about 2 space dimensions or 3 space dimensions? That's exactly the dimensions where the inhomogeneous structures go away. There must be something like generalized Peierls argument, which, as far as I know, is only valid in 1 + 1 dimensions. This beautiful argument about the Fermi surface, and but we just really don't know why 2 space dimensions is so special. Now, these results do not necessarily mean that there's no inhomogeneous phase in QCD. Gauge theories may, after all, behave a bit differently than these effective models. But at least it sheds some doubt on this early conjectures that there may be inhomogeneous phase in QCD, because these conjectures are really based on these effective models. And if you look at the earlier reviews, people really believe that in 3 and 4 dimensions, these models show inhomogeneous phase. You can even find it written in reviews. And it's true if you keep the UV cutoff. But if you remove the cutoff, these structures go away. That is certainly true. So that's I wouldn't say more, but it sheds some doubt on the conjectures about this part of the phase diagram of QCD. Okay, that's it. Thank you very much for listening.
I have a question.
Go ahead.
Yeah, Andreas, are you familiar with Parisi's work on the Gross-Neveu model? And
I cannot understand you. Sorry. Did you understand, Paul? What was the question?
Yes, he was asking about Parisi's work on renormalizing the Gross-Neveu model in 4 dimensions.
Gross-Neveu in 4 dimensions?
Yes.
No, obviously not. No.
Okay.
No. I mean, okay. Are there claims that it is renormalized in 4 dimensions? That's what you say.
Yes.
So there's a famous paper by Parisi in the 1970s entitled "Renormalizing Non-Renormalizable Field Theories."
Yeah.
And where he sort of goes and says that, yeah, perturbatively, you cannot renormalize the Gross-Neveu model in 4 dimensions, but you can do it non-perturbatively in the 1/NF, large NF expansion.
Yeah, no, but I know part of maybe the other side of the story. I mean, there have been many investigations in the meantime, and also this functional renormalization group, which is very much related actually to the large NF expansions. So people have studied the fixed point structure of all these theories, and everything indicates that in 4 dimensions it's not renormalizable. Okay. You could include kinetic term for the scalar field, and then it looks renormalizing in perturbation theory in the large NF expansions. But then you have other problems, lambda poles and so on. But I would be very skeptical about these claims. I mean, we know for sure they are renormalizable in the 1/NF expansion in 3 dimensions, in 3 space dimensions, but not in 4 space dimensions. I will have a look at that, but I mean, I know the modern literature about it, and okay, shouldn't say more. To the best of my knowledge, it's not renormalizable in 4 dimensions.
I'm going to put a link. Can you hear me?
Yeah, sort of. Yeah, okay. Yeah, put very much.
I'm going to put a link to my paper in the chat, and I think you should have a look at it and tell me what you think. We do work with non-polynomial interaction terms, but it is still a Four-Fermi theory. But it's a large NF Four-Fermi theory and a Gross-Neveu model in 3 + 1D.
I think you should just a short question. Just a short question: is it the only 1/n expansion, or is it functional renormalization group methods? What did you do?
It's just the 1/n expansion.
1/n expansion. Okay. I would be very surprised, but okay, I have a look.
Have a look.
Okay. Interesting.
Can you hear me now?
Yes, we can hear you now.
Yes.
Oh, okay, great. So I'm curious about how you calculate these inhomogeneous spaces, because you have a functional determinant with the sigma field, the auxiliary field appearing in it, and how do you? I mean, you're looking for a saddle point of this effective action, and that, I guess I'm confused. How do you calculate the functional determinant? Or do you not?
Yes. There are several ways to do it. One has been, first of all, you have to use, of course, a cutoff. Some calculation have been done in momentum cutoff, also with Pauli-Villars. It doesn't matter too much. Okay, and then you have this functional determinant, which depends on the sigma field. And the assumption is the sigma field only depends on one spatial coordinates. That's the assumption, right? That's a reasonable assumption, by the way. And then you look for the second, and then you make a Fourier expansion of this field, and the determinant depends then on these Fourier coefficients. We cannot calculate it; it's too difficult. But then you take the second derivative of this log determinant with respect to this Fourier coefficient, and this second derivative is calculated at a homogeneous background. So you study the stability of a homogeneous background. You go away from the symmetric phase. And then you can handle it almost analytically. I mean, you have to do numerical calculation, right? You have to take a minimizing problem. You have to do a spectral problem to see all the eigenvalues of the truncated. Of course, you have to truncate it at a certain Fourier mode and check it that it's stable if you include the number of Fourier modes. And then you look for the spectrum of these fluctuation operators. It's non-trivial, but it can be done. Yeah. And then, you know, if you just have one negative mode, you know it's unstable.
Thank you.
So, we lost you again, your voice.
Can I follow up on that question?
Sure.
So do I understand that correctly, that you sort of write down your functional determinant and then you sort of make an ansatz for your sigma field, saying that it's a constant plus a single sign term?
No. That would be enough if you can show instability.
Yes.
If you see that it gets unstable with one Fourier mode, it's fine. But you can make a Fourier expansion, the first 100 cosines or whatever, right? Then you stop at a certain point, and then on this space of these 100 variables, you study the stability problem. That also can be done.
I see.
That's actually what we have done in Jena. We have done a different approach, but since this is not published, I didn't want to mention it. I think we have a more elegant one, but this has been done by the Frankfurt group, what I explained. Alternatively, you can put it on the lattice, making a lattice regularization and repeat the same procedure on the lattice. That also has been done. And the results agree, I should say, of course. In 3 and less dimensions, if you go above 3 dimensions, space-time dimensions, everything becomes regulator dependent. It's you know, if for one cutoff you get the inhomogeneous island and for the other not, and even if you move the cutoff to very high values, you have this discrepancy, which is to me again is a sign that the theories are not renormalizable. I mean, you know, you cannot go to the infinite cutoff in this case. You don't get the unique answer. Okay, but that's another discussion. I will have to look at the paper. Yeah.
Okay, maybe I can ask a question now. Have you considered looking into a theory of non-relativistic fermions, large enough fermions in 4 dimensions? Because
no.
It turns out that if you sort of think about, let's say, the non-relativistic neutrons in 4 dimensions, if you sort of think of NF copies of the neutron, the theory becomes exactly solvable in the large NF limit. And this is, of course, a toy model for the neutron star crust. Again, sort of the naive sort of thing is that they again find a condensate as homogeneous condensate. But I think it would be very interesting given the claims that you have these pasta phases and sort of all kind of non-homogeneous phases in neutron star crusts, to sort of investigate that with your methods.
Yes, good. So these are effective theories again. So we have to keep a cutoff, and
it turns out that no, you had the non-relativistic theory. You can remove the cutoff. It's sort of
remove. Okay.
Yeah, but it's a non-relativistic effective theory. Yes.
Yeah, but you can remove the cutoff. That's helpful, of course, to get the unique answer. Then, yeah.
Yeah. So the four-dimensional non-relativistic field theories have logarithmic divergences only in the odd dimensions, so only in 3 and 5, but only power-like in 2 and 4.
Okay. So I'm sure you have worked on that, I guess, right? Or
yes.
Maybe again you can send me a reference. I would like to look into that.
I will be happy to.
I want to see the physics case as well, of course. I mean, you know, this is so. This I should mention. I mean, you know, as you know, I have been still working a lot on analytic things, not only numerical things. But here you have to think very carefully because such a program goes for 3, 4, 5 years. I mean, so you need a physics case, so to say. But okay.
Yes. Other questions? Okay, I have one more question. So you had this correlator C of X on your slide 19 or so, which was the 2-point correlator of your auxiliary field.
Yeah. Should I show it again? Or?
Sure, why not? Yes.
Yeah.
So this correlation function, this C of X, in these large N theories that we have been studying in our group, there's a curious thing that comes out in the large NF limit, which is that besides the sort of usual properties of this correlator, you predict the presence of a stable bound state in the large NF limit, which shows up as a pole in the Euclidean, in the Minkowski analytic continued version of this.
Yeah. Okay.
I think that similar things should show up in these fermionic theories. So the question is, have you sort of considered looking for a bound state in that correlator?
Yes, we did. You know, on the lattice, you try to. I hope that's what you mean. You try to approach it to mimic it by a massive propagator and rid off the mass from this. And that actually we tried and compared it with a massless propagator and this quasi long range order stuff. And I showed you these figures where we had these huge lattices, right?
Yes.
And we couldn't really distinguish between quasi-long-range order and exponential decay, which would be a massive propagator, and a condensate. It's really, I never have seen that before. It's so, I mean, so the short answer is we don't know. We don't know.
Okay.
Look, it's a correlator on a lattice, which usually in 3+1 dimension you never have. Is 750 essentially lattice points in the spatial direction, a huge lattice, and still we could disentangle the different structures and even the qualitative structures of the if you have x to the minus beta like here, which would be a crossless Soudess transition, it looks almost similar like exponential with a very small mass. It's amazing. I mean. No, we of course we believe it's not massive. To be honest, we believe it's algebraic decay. Yeah.